The last thing to talk about for this material is essentially tying everything together. One other way that we can determine if something is linearly independent or dependent is if our determinant is not equal to 0. And I mentioned this before, but if we look at ax equals b, as long as the determinant of a is not equal to 0, that means that a is invertible, and that means our vectors, it turns out, are linearly independent. If it is equal to 0, then they are dependent. So that's another way we can check for linear dependence or independence. But to bring everything together, I want to look at these two sets of information. So for a matrix A, notice we're talking about ax equals b. We're trying to figure out what types of systems we have, what type of systems and what kind of solutions we can have. So if the vectors of A are linearly independent, and once again, it doesn't matter if they're rows or columns. If they are linearly independent, that means our determinant is not 0. So if our determinant isn't 0, that means our vectors are independent. Okay, so these are equivalent. Which also means if our determinant is not 0, that means A inverse exists. Or A is invertible and non-singular. Which means our system has a unique solution. It doesn't matter what B is, as long as A is invertible. It doesn't matter what B is. It's going to have a unique solution for every single vector in B, or every single B vector that we can put together. Which means that the rank of A equals the rank of AB. It means we end up with our typical, what you've seen in the past, Gauss elimination process. And then one other thing to note is some notation. Homogeneous system, I can't remember if I mentioned this. A homogeneous system is where we have a B vector of zeros. So if we end up with a homogeneous system where B is all zeros, then ax equals b has only the trivial solution. So x is equal to 0. Okay, that's our unique solution in this instance. Okay, so if they're independent, then the inverse exists, the determinant isn't equal to 0, I have a unique solution, and all of my normal stuff that I've seen in the past. Now here's the other side. If my vectors are linearly dependent, it doesn't matter if it's rows or columns, that means the determinant of matrix A is 0, which means matrix A is not invertible, or A inverse does not exist. A is singular. Then I have two options. I either have no solution, or I have an infinite number of solutions. And so I still have those two options. So an infinite number of solutions would look like this. Or here's my RREF, or REF, where I have my row of zeros that goes all the way across. No solution would look something like this, where this is a number. Okay. Note, in both instances, the determinant of A here is equal to 0, because I have my 0 row. And then the homogeneous system has more solutions than just a trivial solution. So my homogeneous system, it would be an infinite number solution. So those are equivalent statements. I created this nice flowchart that helps kind of tie everything together. So you have two scenarios. You have a homogeneous system or non-homogeneous. So homogeneous, all of my B values are 0. Non-homogeneous, some of my B values are not 0. So a homogeneous system is always consistent. And you're going to either have one solution or an infinite number of solutions. You're going to have a unique solution if the determinant of A is not equal to 0, and that unique solution is x equals 0. So you have one unique solution where x equals 0. If the determinant of A is equal to 0, then you have an infinite number of solutions. For a non-homogeneous system, it's either going to be consistent or inconsistent. It's going to be inconsistent if the determinant of A is equal to 0 and the rank of A is less than the rank of AB. It's consistent that shouldn't be there. It's consistent if the rank of A equals rank of AB. It's unique if my determinant is not equal to 0, and it's infinite if my determinant of A is equal to 0. So there's a couple ways you can essentially play around with this flowchart. You can think about it in terms of the rank. The rank shows up in all of these situations. The rank of A and AB will really tell you a lot. But the determinant also gives you some information. So as long as you know some of those pieces, you should be able to determine it's a consistent system, an inconsistent system, one solution, infinite number of solutions, or no solution.